about to start the first real process of putting this engine together, which is assembling the connecting rods onto the crank. But before I do that, I have to make sure all of them are within spec as far as their size. And that entails measuring the big end and small end of the connecting rods, as well as the bearing size of all the main bearings and the conrod bearings on the crankshaft. One tip that I've found really valuable and helpful is not only getting the right tools to do this, but getting them rather cheaply. And I'd highly recommend going on eBay and finding used sets of the, I would say, non-standard type garage tools that you might use for a project like this. So for me, I didn't have a set of micrometers, and so I was able to get this set. I have 3 sizes, a 0 to 1 inch, 1 to 2 inches, and 2 to 3 inches. And these were brand new Mitutoyo micrometers that I think were made around the 1980s or the 1970s, but they were new old stock. And so I got them, they were a complete kit, nothing wrong with them, and I got them substantially cheaper than what you could get a new set for. The other nice tools for this job that I got were these telescoping bore gauges. And the way these work is you put them inside, or you first contract this telescope, and there's a little friction clamp there, and then you put them inside a bore, and you can extend the arms. This one's a little sticky, it needs to be lubricated, and then figure out what the bore size is. I'd never used these before I bought these, and I think they're a really handy tool, and they weren't that expensive. These, again, were probably made in the 70s or 80s, but any of these tools, if you take care of them, they'll last forever. But the way it works is you put it inside the bore, you undo the friction clamps, so now the gauge is hitting the bore, and you allow it to expand, it hits the bore, you make sure it's perpendicular, and then you close the friction clamp, and you can tip it and bring it out. And the faces of these are slightly spherical, so they enable you to tip while still maintaining contact, and if you tip a little more, you can bring it out. Then what you can do is put it inside your dial indicator, your micrometer, and measure what this distance is. So, yeah, this is a nice setup, and enabled me to measure all the bearing sizes pretty accurately. Another thing that I did that was pretty helpful is I made a spreadsheet. I'll show it right here. I made a spreadsheet of all the sizes of all the bearings that I measured to see if they're in spec or not. And so, these values of the upper and lower limits of the bearing sizes are out of Dempsey's book. And then the spreadsheet here enables me first to measure in inches. All my tools are in inches. Then I convert to millimeters. And then I just set up a simple if and function if the measurement is in between the upper and lower limits specified by Dempsey's book, and it'll return a yes or no. And so the crankshaft bearings are all good, but this is a little concerning that the inside diameter of the big end of the connecting rods is actually not in spec in some cases. So I need to investigate that a little more. I think it's because the rods are probably cranked down and fully tightened, because that's how my machinist machined them, as he should have, so they're round under load. So I got to investigate that a little more. But everything else is turning out to be in spec. The main crankshaft bearings, all 7, are looking good, as well as the bearing at the end, the number 8 bearing, looks good. So this is just it was a helpful tool for me. You could just write this down on a piece of paper too, but it enabled me to organize everything. The other thing I did too is you could see I labeled the cylinders 1 through 6 and their corresponding connecting rods and bearings on the crankshaft. And then also the main bearings, I labeled them to their position between the cylinders. And so this is important because here's the cylinder layout, and going from the crankshaft, you know, the number 3 cylinder is closest, and so it goes 3, 6, 2, 5, 1, 4. So I laid it out that way, and I'm trying to keep all the rods matched with the bearings on the crankshaft that they go with. When I took the engine apart, actually, just with you can probably see it on some of these. I've put Sharpie over them now, but just I scored in Roman numerals what number pistons each rod went with, and so I can keep all the parts matched. I don't think that really matters because I'm changing the bearings anyway. Here are the new rod bearings, but yeah, it doesn't hurt. So I'm going to keep the rods where they were. My crankshaft fortunately didn't need to be repolished. It was in great shape. My machinist, and I agree, felt that the bearings were in quite good shape and weren't really scuffed up. So he may have sanded them a little bit or polished them a little bit, but all in all, they're in really good condition. All right, let's take a second and talk about why measuring the bearing clearance is so important and how cool the bearings are in a car engine. So the journal bearings that support the connecting rods and the crankshaft are what are called hydrodynamic journal bearings. And what's so cool about them is that, opposed to like a ball bearing that has rolling elements, balls that allow a shaft to turn, the crankshaft is essentially floating on a film of oil. So there's no mechanical contact when the engine's running. And the way that looks is that if you look at one of the bearings, here's say the journal bearing, the shaft of the crankshaft, and then it sits within the journal bearing in the case or in the big end of the rod. And so let's say the crankshaft's turning in this direction at an angular velocity we can call omega, and that journal has a radius r, and what we're typically measuring is diameters, the diameter of the inside and the diameter of the outside. What that means is that at the surface of this bearing, we're going to have a tangential velocity of omega r. And why that's important is that on the outside of the bearing, where your bearing inserts go, you have a velocity of 0. Now, what that means is that that fluid, as it's getting churned and turned within the bearing, it goes from having a velocity of omega r down to a velocity of 0. And the reason is that any what's called a Newtonian fluid, any typically behaving fluid, will obey what's called a non-slip boundary condition, meaning that the little molecules of fluid right on a surface are going to have to move with that surface or be stationary with that surface. So what that creates is a velocity field where your velocity of the fluid goes from omega r at the inside of the bearing to 0 on the outside. And so you can imagine that as this is turning, you're actually getting a movement of fluid around. If you think about it, say, in a horizontal scenario, and we move, say, a top surface of a channel at some velocity v, and here it's 0, you're going to get that same flow profile. This is called a Couette flow in fluid mechanics. And you can imagine that as you're moving this top surface, you're going to be dragging fluid along. And so you get some net volumetric fluid flow. Just over time, fluid's going to migrate in the left direction in this case. So what that means is that as this bearing turns, you're getting fluid that's circulating around and around. Now, what's really cool about these bearings is that when you apply a load to them, so let's say during the power stroke of the bearing, you've got this big force coming down from the conrod. What happens is that the crankshaft, the inside of the bearing, actually is going to shift a little bit. And it's going to shift down like this. And it creates a smaller channel right here at the bottom, where now, as this fluid is flowing through, it has to pump this fluid, it has to pull this fluid through, and it has to go into this small gap. And so it's just like kind of blowing fluid through like a straw or something where there's a restriction. And to get this fluid through, you need a pressure that builds up to force it through this smaller gap. And so what you end up having is, let's see if I can draw it in purple maybe to distinguish this. You end up getting a pressure profile over the bottom here that looks something, roughly like this, where here's our pressure as we move across horizontally in the bearing, say in this X direction. And so what that pressure does is that pressure pushing back on the crankshaft supports the force being applied to it. So what's so cool about this is it's not like an actively, yes, you have an oil pump, but the oil pump is really supplying oil to this region. But as long as you have fluid within this little gap and are turning this around and around and around, as soon as you offset that central shaft, in this case the bearing on the crankshaft, as soon as you offset it, you create this smaller gap in the bearing film, which requires an increase in pressure to push the fluid through that film, and that increase in pressure in the fluid reacts on the shaft to counteract the force. That is the coolest thing. And so in theory, you could run a hydrodynamic bearing forever, right? As long as you're supplying fluid in here and it's clean, it'll go on and on and on. Now, why measuring your bearing clearances is so important is that the clearance here is on the order of like 0.01 millimeters. It's really, really small, about 1/100th of a millimeter. The overall diameter difference can be anywhere from 100th to like 7/100ths of a millimeter, but in either case, it's on that order and it's really small. A human hair is around I think it's around 6/100ths of a millimeter. So, you can basically fit a human hair into here and it would potentially jam, it would get churned up because the hair's not that hard. But it would basically fill up all the gap between your crankshaft and the outside of your bearing. So the second reason you have to be concerned about these clearances and keep your bearings really clean is that if you get any junk in here, and really small particulates of like dust or metal or anything hard like concrete or rocks, it can really dig up the bearing surfaces. So this is why you have to be so meticulous when you're assembling your bearing so you avoid any contamination in here. But I think this is just the coolest thing, and whoever thought of this was brilliant, because you're essentially making a pump by the rotation of the shaft. And if you design it right, I've heard about like transatlantic ships that can run for like a century, because they're just basically running all the time back and forth, and always keeping this lubrication layer in the bearing, so you're never making mechanical contact. And that's another good point. Where engines like really get harmed is when they have a starvation of oil in this bearing film. So that can happen on startup of the engine, where if the engine's not running and you've lost your oil in here and it's allowed to just settle out, you will have mechanical contact between the crankshaft and the bearing journal. And also this can happen if you've ever spun a rod bearing. If you lose lubrication, if you're not supplying oil fast enough and this squeezes out over time, you can also get mechanical contact and wreck your bearing. I'm using a technique to set up my crankshaft, which is suggested in Dempsey's book, where you just take 2 flywheel bolts, and I'm using old bolts that I'll throw away, and mount your flywheel on your crankshaft, so then you can turn it upside down and you have a nice pedestal to stand up the crankshaft and have it supported vertically. That worked well. Another word of caution: always clean, clean, clean like crazy. I'm finding particulates on stuff, and you want to really be fastidious about cleaning everything off. Also, I'm going to reuse my old flywheel in this build because it's good. It was okay. It wasn't too scuffed up from the clutch, and my machinist was able to refinish it and balance it, and it's good to go, and that saves some money. So I realized that the conrods I got back from my machinist were already torqued down, and I'm glad he did this, because when he machined the bores of the conrod, they were fully clamped. The metal had deformed because of that loading, and so when you cut a circular shape, it stays perfectly circular even when under load. So when I unclamp these, they will pop back. I had to make a set of soft jaws for my vise. I didn't want to use the teeth of the vise to hold the face of the conrods. That would mar it up. But so using aluminum makes it totally safe. Another point I want to make about the conrods is I can unbolt and rebolt these because I'm using ARP rod bolts. These are made to be able to be reusable. Typical, I guess, older style rod bolts would plastically deform. They'd actually permanently stretch a little bit when you torqued them down, but these do not do that. So I can unbolt these and rebolt them through this measurement process without any fear of hurting them. I've done the plastic gauge clearance measurement on the first two cylinders, cylinder, 3 and 6. And so now I want to go through the whole process with cylinder 2, just to show what all the parts are. It's actually a lot simpler than I thought it was. And I wanted to comment also going through this process that I've certainly been intimidated by parts of this. I know I'm going to get into a lot more complication putting together the engine. But I think it's reassuring to, again, experience that, even complicated tasks, you take one step at a time, and they turn out to not be so bad. I've never done this type of work. I've never used plastic gauge. I've never tightened down conrod bolts. But it's all pretty straightforward, and it's not too bad. And it's kind of like a big Lego kit where you have to be super careful and clean, but still kind of the same idea. Anyway, to put together the conrods, first what I've been doing is cleaning everything, which you got to do over and over and over. So I have this is conrod number 2 for cylinder number 2. One reason I'm keeping the conrods with their bearing on the crankshaft is that I know they fit. They ran there for 100 and something thousand miles, and for almost 40 years, and so why mess with it? So anyway, clean those first, and you want to clean the bearing. So cylinder 2 is the third bearing up on the crankshaft, so right here, almost in the center. So clean that really well with isopropyl alcohol and clean wipes. You can see there's gunk on there. I think part of it is from the counterweights, but either way, you want it nice and clean. And then clean off the conrod itself. And both sides and the bearing. I'm not going to re-lubricate the threads. The threads have lubricant on them from when my machinist tightened them down. I'm going to lubricate them once more when I tighten them down for the final assembly. But for now, I think there's enough lubricant on them to be fine. And wipe off the bushings. In the case, I've seen that the impression of the bearing stamping on the backside has been forever marked into the case, which is kind of cool from being there for so long, for so many years. So these are all cleaned off. Now I can assemble the parts, and it's I think it'd be hard to assemble these the wrong way, but there's a small key in the bearing. I don't know if you can see that. That just slots into a key slot in the journal. And you have to rotate them a little bit. They kind of just snap in. What I've noticed too is that there can be some small shavings of the bearing material that can get cut as you put it in. So I've been doing one last wipe as well. As I do that final assembly, just to make sure there's no metal shavings in there that could mar anything up. This oil drip pan, by the way, is quite clean. I've been cleaning it a lot. I just blew it off before I did this because there is just junk that falls off the ceiling in my garage and other stuff that comes off the crankshaft. So those are all set. Now what I do is I can put the con rod in on the bearing. So third one up. And just slide that in. And then put a piece of plastic gauge on the other side. This stuff's great. I didn't even know this existed before I used it for this project. But it's really a fine strand. I'm not sure if you can see that. But you can put that over the bearing surface. And I've found that if I kind of cinch the sides, I can kind of make it a C shape and press it into the sharper edges of the bearing so it stays in place. So I think you can be able to see it there. And that way it stays on as I put the bearing cap in. So I put that on. And I just put it on backwards. Good, the plastic gauge stayed. But you have to make sure that you line up the sides with the numbers with on both sides of the con rod. So I was backwards, but now I got it. And now we can put the bolts on. Or sorry, the nuts. Oh, another thing that I realized doing this is make sure you clean your tools. My socket, I have a 12-sided socket, you know, this one, just common Craftsman socket that I'm using to tighten these down. And I've had it for, God, decades. And it had so much junk built up inside it. I actually took it down to the parts washer and washed it out. So now it's quite clean. In Dempsey's book, he talks about when you tighten this down, be careful not to smear the plastic gauge. I haven't found that's a problem yet. I think it's pretty good, pretty robust to smearing. So here's my torque wrench, and what I've been doing actually is tightening both bolts down to 25 foot-pounds first. The ARP guide says to do 50, and I'm doing it in 2 stages. And the reason is I want everything to seat well, and I don't want to over-tighten one side versus the other. And I also want to make sure when I do the last torque down, I have enough throw to torque it while the nut is still sliding on the grease. And that's in order to tighten it down so when you're in a dynamic friction situation, not static friction. If you get it almost tight and stop, and then try to tighten it again, your torque wrench will click because it'll take more torque to break away the static friction. So just be mindful of that. I'm going to stand up for this. I'm going to have to screw this down a little bit first just to seat the bolt head. So that's seated. I'm going to do the other side. Probably could use a smaller wrench to do this, but I got to use a torque wrench in a second anyway. Okay, so that's seated down. And now I can do the first torque step of 25 foot-pounds, which I think will come during this throw. There we go. One side, let's do the other side. Good. And now, here's where I'm glad I measured my torque wrench values before I did this project. With the calibration I did, I actually want to crank this up to only 43 foot-pounds indicated on the torque wrench, which when actually applied to the bolt in the nut will convert to 50 foot-pounds. Because I measured there's about a 16% error in what the indicator on the torque wrench reads and what I'm actually applying. So there's 43 foot-pounds. And so I'm going to do each side now. And it's a little wonky to hold. Oops. Just double check that. Didn't move it. No. Good. I've had to do this in 2 strokes sometimes. So I'm going to go down part way. And now I should be able to do a full stroke to the click. There we go. There's one. And the other side. Take a little bit first. Now, there's the second. I just finished tightening down this con rod and using plastic gauge to figure out the gap clearance. I've never used plastic gauge before. This is pretty cool. And it worked great. You can see the green strip right there of the flattened out plastic. And what you do is you just hold this up, this scale up, and you can see that we're a little narrower than the .038 portion of the scale, which means the gap's a little wider than that, but it's definitely less than .051. And that's great because the gap's supposed to be anywhere from .03 to .088. So we're right in that sweet spot. And this con rod is good to go. Something I've been hemming and hawing about is how to check the clearances of the main crankshaft bearings. I think the proper way to do it would be to use plastic gauge on every main bearing in the crankcase, put the crankshaft in, and then bolt the case together completely. And my mechanic suggested doing that except without the crankshaft in it because you could use a bore gauge to measure the bearing diameter all the way down the case. Now the problem with that for me, I don't have a bore gauge that long. I only have the small telescoping gauges. The other thing I don't know about is if there's any plastic deformation that happens in the bearings when you clamp the case together. Also, in Wayne Dempsey's book, he doesn't recommend to do this. I did measure the main bearing diameters of the crankshaft, and all those check out fine. So I'm wondering what to do, and I think just as kind of a gut check, it's worth taking my main bearing set, which is right here, opening it up and just measuring what is the thickness of each of these. Now, the diameter of the crankshaft on the main bearings is about 60 millimeters. And the bore size in the block where these bearings are held is supposed to be about 65 millimeters. And so that means each of these, and this is neglecting gaps for lubrication, but it means each of these bearings should be about 2.5 millimeters thick. And so I think it's worthwhile at least taking a set of vernier calipers and just as a gut check figuring out what these are. So these are measuring, I guess drum roll, yeah, 2.49 millimeters. So that's a pretty good gut check. I didn't do any machining on the case, didn't do any machining on the crank. And so I think if there were clearance issues, it would be due to the bearings. And given that these bearings seem to check out just fine, that's a worthwhile quick test, at least to let me sleep better tonight, and move forward with the assembly without fear that I'm going to screw something up. So what I'm doing now is really trying to meticulously clean all of the bearing surfaces that are going to mate. in a few minutes when I bolt this thing together. And so even though I've cleaned these what seems like 100 times, I'm still going over again all the bearing surfaces on the crank. And then right here I've got all the con rods laid out, and I'm going to go through all those. Then I'm going to apply assembly lube to all of them and then bolt them on. Again, I kept this surface really clean. I cleaned off the oil drip pan again, and there's just little particles everywhere, unfortunately. Even these clean wipes, they're good, but they're not foolproof, at least for this fool. So just be careful, keep an eye out for fibers, and clean, 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 clean. I'm using rubbing alcohol right now, isopropyl alcohol, just to do this last clean. I've cleaned all the parts again, meticulously really cleaning off all the bearing surfaces on the rods, as well as the grease that was used on the bolt threads. I'm going to reapply that with this ARP assembly lube again. And now it's time to actually use real assembly lube. I've never done this before, but the name of the game apparently is you spread a little bit. Oh, not that much. I just had a bunch come out on my fingers. Try to suck that back in a little bit. But you spread a bit on the bearing surfaces. This is less viscous than I thought it would be. But you're supposed to do a uniform layer on the surfaces, which isn't too bad. And I'm going to do all the rod pieces first and then put them together. Yeah, this isn't so bad. So go down the line and do each piece. Man, this is messy. Watch out, it comes out fast when you open a new bottle. But there we go, seems to be working. And it really doesn't matter if you spill it over. It's not like there's any thickness associated with this once you clamp it down, and all this is washed away by the lubrication system of the engine anyway. So, cool. I'll keep working down the line here. And I don't think this had to be mixed up at all. Hopefully not. I tried to do it. It looks like it separated a little bit. It looks like there's oil and then maybe a grease compound mixed together. But this is good. This is fun too. I've never done this. It is like a huge Lego kit. And I love just seeing everything laid out, all clean, and looks, it's not new, but it's in good shape. Parts are new. Yeah, good. I'll keep going on that. Okay, so now it's the time for the big finish, to assemble all these together. So here is Conrod 3. I'm going to do it so the numbers are near me. Put a little lube on the threads. Try to spread it out a little bit. So it doesn't go everywhere when I stick it through. And then I'll wipe it a little bit on the nut. Alright, so here's bearing 3 at the bottom here. It's the one closest to the crank, just double checking my figure. So let's slide this guy on. Great. And then making sure the numbers are facing me. That's correct. There is an orientation to these you want to get right. Numbers, numbers. And then put a little bit of grease on the nuts, on the nut face, which ARP says you need to do. I think I probably put way too much grease on these, but we'll see. That's okay. Better more than less in this case. A little bit more on this nut. And it's on the face. And then the last step is to torque it. Use a bit shorter extension. My torque wrench, just double checking, is at 43 foot-pounds. Looks good. So I'm going to do this in a few stages. Get a little tight. Get this side a bit tight. What's nice is I can turn this freely now. I don't have to worry about smearing the plastic gauge. Starting to get tight. All right, and now the click. Let's tighten this sucker down. Oops, get the socket on a little better. There we go. There we go. Whew, almost ran out of throw there. There's one. And I guess, let me go this way. I'm actually going to put the bigger extension on. I like that better. Because I can turn past the head. There we go. Cool. And just to make sure this first side's tight, do it one more time. It should not move and just click. There we go. Yep. Great. And you can check that it's the correct amount of gap, that this thing should just kind of fall slowly under gravity, which it does well. Woohoo! All right. This is exciting. I have never, ever done this before, and it feels pretty good to feel the conrod there and feel the friction, well, not friction, but the viscosity of the, which is like friction, but the viscosity of the lubricant, the assembly lube. I think that's how it's supposed to feel. All right, on to the next one. First significant step done. I just finished torquing down all the rod bolts here, and they feel good. They all have about the same amount of damping, resistance to turning. There's no like grittiness or anything in how they feel. So I think they're good. I think process worked. The clearances of all of them work out great. And now we can move on to the big part of the show, the crankcase assembly. I'm pretty happy with this, and I think this is a nice barrier to get over, and confidence builder. And I think it's worth saying again, you know, taking baby steps and building up your confidence in a project like this really helps. I started doing this working on an old motorcycle I had, still have, and just doing valve adjustments, just cracking open the valve covers, adjusting the tappet clearance, and having that my first experience actually getting into the motor and the oily bits and the precision stuff, and realizing that, yeah, I can manipulate that, I can fix it, and it can still work, and I didn't screw it up. And so over years, you get to this, and yeah, I feel really good about this. It's not rocket science. It's not easy. It's not Legos, but it's tractable. And man, it feels pretty good to see, after the big teardown of many weeks, to start moving in the other direction and start putting it together.